you're going to rewrite this as a sine over a cosine. And then now that we've created a fraction, that's why it falls underneath the u substitution section. So when we go to pick our u, this one you want to be a little bit careful of, and if we had a little more time, because I want to make sure we get done with this, most people pick sine of x. So don't pick sine of x, just kind of pay attention as to why this doesn't work. What we get from that derivative is cosine of x times our dx. If I do this substitution, this is my numerator. What I now have is, or left over, is a cosine of x in the denominator and a dx. So if you look at what we created here, don't we have the cosine of x being multiplied by a dx? Whereas if we look over here, what you really have over here, I could just as easily put the dx in the numerator. This is a dx being divided by x. So the product of those two is obviously not the same as the quotient of those two. So that doesn't work. So what we have to do with this is we've got to let u be the cosine. So let u be the denominator. The derivative of that gives us a negative sine of x times dx. That is what we needed now, because this is a sine of x that is getting multiplied by dx. We talked yesterday a bunch of times, we don't want the negative in this problem, so you multiply that over to create the positive sine of x times your dx. So what you are then left with, our u is our denominator, and then that sine of x dx, all right, that I have highlighted in yellow, we can get rid of all of that if I replace it with a negative du. That should be recognizable to us as the natural log, absolute value of u, plus our constant. And then plug back in your u, the antiderivative of tangent we just found to be this. So long term, now that we have done this, you already know the antiderivative of cosine. We've done this. You already know the antiderivative of sine. We didn't really have to think too much about that. Now that we know the antiderivative of tangent is a negative ln, you really could just skip all those steps and just jump right to there. It's another thing that if you can get it memorized, it just makes that a whole lot quicker of a process. Same thing with number 13. We're going to go through number 13 all the way, but eventually you want to kind of just figure out what is the antiderivative of cotangent and then just have it memorized, what we find it to be here in a second. And that'll save you some problems on down the road, or at least save you some time. What I'm showing you, though, if you ever do forget these, is a process that will always work. If you just know we got to rewrite them and go through u substitution, that will always work if you do forget these antiderivatives. So 13, same process, rewrite it. The only thing that's going to work is if your u is your denominator, because the derivative of that will give us cosine of x times dx, which is what we have in the numerator. So the u is our denominator, cosine of x dx, that works out to be perfectly the du. Now we don't have any sign issues, so we get another 1 over u, which means we get another natural log absolute value of u. But now our u is sine of x. Okay. They're similar. I always kind of, when I kind of just get these memorized, this one's negative. If you know that, then know this one's positive, so they're the opposite. Same here. If this is a cosine, kind of the opposite of the cosine is our sine in terms of the two that we deal with a lot. There should be else, as I'm rushing through, I forgot something here. Also go back to number 12 and put a little or right here, because you will see this antiderivative written a little bit differently sometimes, and you want to recognize that. This could also be written as a positive natural log of secant plus c. Understand why that's possible. It's just our log rules. Like if I gave you 2 natural log of 3, can't we make this to the power of the 3? And then that's a natural log of 9. It's the same with this. So I can take this negative, which is really a negative 1. I can make it the power of my cosine. So that's why the log becomes positive. And then if I put the little negative 1 here, that means I want the reciprocal of cosine. And the reciprocal of cosine is secant. So you kind of want to know both. Those do both pop up in both ways. So just know they're equivalent to each other. So it's a different way of expressing them. Okay. All right. So those, a couple more things that you probably just want to get memorized. All right. Next page. 14. Similar to the trig function, sine and cosine tangents, whenever you have a power with a natural log, if you were doing a derivative, I would recommend rewriting this. If we're doing an antiderivative, I would recommend rewriting this. Because once it is rewritten, I think it's pretty obvious now. Like if you would have looked at it originally, you might have found that weird, harder. Once I've rewritten this, I think you can look at this now, hopefully, and pick out what our u would be pretty quickly. You have an inside term. So if all else fails and you're still not sure, pick the inside part. The derivative of this is 1 over x and a dx. So if I could slide a 1 in front of here, that's what we have, 1 over x dx. So what we would have ended up with is a u to the 6th. So our inside term is now our u. And then I do have a 1 over an x and a dx, and that's what we got here. So we can get rid of all of that by putting in our du. Easy little antiderivative, u to the 7th over a 7. Replace your u with the natural log of x. And then that's our answer. All right, easy enough. 15 should hopefully be nice at this point. Rewrite this as sine of x all to the 4th power. That gives us now a clear inside term. If you think ahead a step, if you let u be the inside term of sine of x, the derivative is cosine of x, which is what we also needed. So let u be sine of x, du is cosine x dx. So we now have u to the 4th. The cosine of x dx is gone with our du substitution. And then again, pretty simple derivative here, our antiderivative. So our final answer would be sine, I'll put the 5 here, sine to the 5th of x over a 5, and then plus our constant. $16 I'm going to leave you. I'm going to hope by the end of the day, if you went back and tried 16 on your own, you would think 16 is very easy. So we're going to move along to number 17. 17 is different. We haven't done one like this yet. Regular logs. So a long time ago when we did the derivative of these, what I always told you is we always want to rewrite a common log using natural logs, using the change of base formula. It's one of another property from last year. Same holds true with an antiderivative. Pretty much anytime you have a common log, we're going to rewrite this. So I'm going to rewrite the log base 2 of x as the natural log of x over the natural log of 2. We would have done that with the derivative. You're going to do the same thing with the antiderivative. That whole thing then is divided by the x. You still have x in your denominator. Simplify this. We certainly don't want to be dealing with that type of a fraction, a complex fraction. So just simplify this. This ends up being natural log of x over x times the natural log of 2. To make this, again, something simpler and easier, understand the natural log of 2 is a number. You could throw that into the calculator. It's going to spit out a value. So because that is a number, it's a constant, we could pull this out. And I would recommend doing that. I'm going to pull that out. It's in a denominator, so when I pull it out, make sure it remains in a denominator. So that constant we're going to remove. And once that is done, I would hope now, if we're understanding how u substitution works, the whole process, when you look at what's left over, this should be a nice setup for everybody. We could hopefully look at that. What would we want u to equal so that the derivative gives us some other parts, and then it becomes a pretty nice little problem. So for this one, hopefully we would understand if we let, I have a lot of space here, squeeze it in. If we let u be the natural log of x, du is 1 over x, and then your dx. So all I would get is a u in the numerator, and then I would have initially had 1 over x dx left over, but that is the derivative. So all that is pretty much going to go away when we replace it with a du. U squared over 2 plus your constant. And then now we have the natural log of x quantity squared as we substitute back in what our u was. This would be 2 ln of 2 plus our constant for sure. If it were multiple choice, I'm going to take that 2, I'm going to make it the power of the 2. So it's going to be the natural log of 2 squared. So our simplified version of this would have a natural log of 4 in the denominator. Okay, so this ends up being our guy. Now, I rushed through those because I want to make sure we got to these now. So if you now notice, we're dealing with definite integrals. So we start having limits to these. The first 17 problems, we didn't worry about any limits. Now we have them. So I wanted to make sure we got to these. Start this problem off as if there aren't any limits. So you can kind of just ignore these right now. So let's see if we can pick out our u, pretend those aren't there. Do your derivative. These will start out the same way the first 17 problems would have started out. But don't go too far. Oh, what am I doing? All right, hopefully we all agree u is going to be tangent, because then the derivative of tangent very nicely gives you the secant squared. So this actually is one of the other 10%. Like the tangent isn't the inside part, but hopefully pretty obvious there. If we let u be tangent, the derivative gives us everything else. So we come back over here. Tangent of x ends up being your u, and then the secant squared of x dx is our du. So we now have a product of just the u times the du. We do have limits, however. So here's now what we want to understand about these two limits here. So over here, I wrote this problem. We all know how to do, super easy. We would do the antiderivative of this. You would get x squared, and then you're going to evaluate it from 0 to 2. Then we would know we want to take this 2. We're going to plug that in for x. Then I'm going to take the 0. I'm going to plug it in for x. So if I'm plugging these values in for x, wouldn't 2 and 0 both be implied to be x values? Yes. So if we look at this original problem that we are dealing with the variable x currently. That is implied to mean that the 0 is an x value and the pi over 4 is an x value. We can't then be putting x limits here and here if we're now dealing with the variable u. So what now has to happen is these need to get changed. So the way we're going to change them, we want to put them in terms of u. So it would be very, very nice if we had a way to convert x's into u's, a relationship between our u's and our x's, so that we can convert those, right? We do, because if we just look right here, isn't u going to always be the tangent of whatever our x is? So if I take this lower limit of 0, get rid of this one, money eraser. So our original lower limit had an x value of 0. So I'm going to come over here to the x value in this equation, and I'm going to substitute in the x value of 0. Because u is the tangent of whatever x is going to be. X is initially a 0. So the tangent of 0 ends up being a 0. So that actually stays the same. But I need to do the same thing with my upper limit. My upper limit had an x value of pi over 4. So that means I need to go back into this equation here. And then where I had my x, I need to plug in the pi over 4. This one now does change. The tangent of pi over 4, that's our root 2 over 2's, and we're dividing them. So root 2 over 2 divided by root 2 over 2 is a 1. That's the first thing that's different. There's two things that differ a little bit with the first 17 problems. One, now we got to get our new limits from x's to u's. The next step is the same. You're going to do your antiderivative just like we would normally, and we're now going to evaluate from 0 to 1. The second thing that is different, aren't these now u values? That's the whole point of us doing that substitution. So what we don't want to now do, we don't want to go back to the u that we had at the beginning. We don't now want to take this and plug it back in right here, because we have u's that would have to now get plugged in for x's. So we don't have to substitute back in the original function right now. We just execute like you would have done on the test a couple of days ago. Just take your 1 and plug it in right away. Subtract, take your 0 and plug it in. And then whatever that evaluates to be is our answer. So that should give us a 1/2. Okay, follow that process, sort of. Okay. 19, same thing then. Do the u part. This should also be, hopefully now, in our 19th problem, although we did skip a few, but still, this should be one that we can look at and say, yeah, u is going to be this, du is going to be this. That part we should have hopefully down pat pretty well. All right, so u definitely just the x cubed plus 1. The derivative of that gives us everything else in that integral so that we're all set there. So we just get root u du. These are, again, x values. They were intended to be plug in for the variable x. We no longer have the variable x, so we want to convert them. We can always do that with our substitution here. So if you take the -1, plug it in for x over here, what we would get is u to equal the -1 cubed plus a 1. Our new lower limit should be a 0. Same thing with the upper limit. The upper limit was an x value of 1. So if we take that 1 and plug it in over here, our upper limit becomes a 2. From there, it's just like what we've been doing now for the last couple weeks. You're going to do the antiderivative, plug in 2, plug in 0, figure out what their difference is. So this is a 1/2 power, so you're going to get u to the 3/2 divided by 3/2, so times 2/3. Plug in your upper limit. I'm going to simplify this also. This is the square root of u cubed, so that's going to be the square root of 2 cubed, so root 8. Plug in your 0. That's going to be the square root of 0 cubed, which is still a 0. So AP test-wise, this is why I won't make a big deal either. Like if it's a free response quiz, test, just open-ended, you can leave this. They don't mark off for you not simplifying. They actually don't want you to simplify, because if you simplify this wrong, they're going to take off a point. You can just leave this. Multiple choice, though, it is going to get simplified. So do make sure, I mean, we know, hopefully know how to rationalize something like this, or not rationalize it, but simplify it. That should then give us 4 root 3 over root 2. That would be our multiple choice answer that we'd be looking for. So this version is fine. This is our reduced version, or simplified version. All right, 20. Do the u real quick. Again, I'm hoping the u's are becoming very obvious to you. Actually, see if you can finish it. This is a nice one. You get a nice number A lot of cool math stuff happens. Some things I'd like to make sure we remember anyway. So see if we can go all the way through that, see what you get. And a lot of times when you get this answer, it's a pretty good indication that you're correct. Stuff works out like this. We all get that answer? Pretty sure, if I remember correctly. Should get a 1. Okay. Our u would have been the ln of x. Our derivative gives us a 1 over x and a dx. So the u is your denominator, because that's where the natural log is at. And then the 1 over x dx will all be gone by replacing it with a du. So we just get a 1. Get your new limits. Here's how we can do that, this substitution. So this is what I was referring to. So if you remember all this, the natural log of e, we should have gotten to be a 1. If you take your e to the e and plug it in, that should just give us a nice e. Heads up also, on the quiz, on the test, in many questions, I just have you stop right here. So some of the questions I might ask on the quiz and on the test when we eventually get to it when we get back, I'll just ask you which integral is equivalent to this one. And all I'm looking for is this here. Can you write everything in terms of u? And sometimes that's it. You'll just stop the problem. That's the one that you're going to be looking for. So be prepared for that. Don't get thrown off by that question. Here, we're going to finish it. We're going to do our absolute value of u, natural log. We're going to evaluate it from 1 to e, and then some more values that we should hopefully remember. The natural log of e gives us this 1, and the natural log of 1 gives us a 0, and then that's why we get our 1. Okay? Okay, 2. Again, super easy substitution here. So this we can go through very quickly. Oops, I'm thinking ahead of step. So our u should be x squared minus a 5. Du is then the 2x dx. So a lot of natural logs happening right now. So this should be a 1 over u du. Get your new limit. So take the 0, plug it in over here to convert it. And our new lower limit should become a negative 5. Take your 2, plug it in. Should get a negative 1 for your upper limit. So now finally, the first problem where I can talk and we hopefully know enough to understand why the absolute values are important when we do this problem with the natural log. So think about what this question is asking us. Here's what this graph looks like. 1 over u looks like this. Okay, think of it as 1 over x. Okay, it's 1 over u. Think about our intervals. Let's say this is a negative 5. Let's say this is a negative 1. Recall, integrals are basically asking us for our area, right? Integrals are the area. So do we very clearly have area enclosed by this curve and a negative 1? Is there area there? Yes. So we better have an answer to this question. We have to, because there's clearly a negative amount of area underneath this curve. So if I took this antiderivative and I don't use a natural log at this point, we have a problem, because I'm going to now plug in the upper limit, use parentheses, and the lower limit. Can we take the natural log of negative numbers? No. And if we tried to, we would say that this is undefined. We can't take the natural log of negative numbers. So what we've done is we've restricted our domain from this problem here, our domain is everything but 0. And then our natural log is only positive numbers. It doesn't take into account the negatives. So that is why, since the original function has a domain that's positive and negative, just exclude the 0, we have to have those those absolute values in our natural log, so that we will get, it's up to you how you want to handle this actually. You could do the natural log of 1 minus the natural log of 5. And then you could use your rule that when I subtract natural logs, we divide their insides. So that's one way to get the natural log of 1 over 5. If you remember the natural log of 1 is 0, then what's going to happen is this guy would drop out. And then you would just want to make sure we understood how does this become a natural log of 1/5. And that's just, again, similar to that trig function earlier, the tangent. I can take this -1 and make it the power of that 5. So now that's why it becomes a positive natural log, and then 5 to the -1 is a 1/5 fraction. Okay, so natural log of 1/5 is our answer either way. Okay, 22. Do 22. So the reason I wanted you to try this on your own is because there's 2 routes you could take here. The route I am going to take, and then long term, hopefully what everybody would take. We just did it. My computer will move. Remember we said, well, now that we've done the tangent, we don't have to go through all of this work anymore. That the antiderivative of tangent, we just skip all these steps and come right on down to here, is either the negative ln of cosine or the natural log of secant. So when I do this problem, we don't have to do u substitution for this because we now know it's antiderivative. We can jump right to the negative natural log of cosine if we know that. The reason I use cosine is because usually when you have limits, you want to think of evaluating it in terms of cosine anyway. So if you were to put the natural log of secant, that's fine. But when you now have to evaluate it, like the secant of pi over 3, you're going to probably have to think cosine anyway, like 1 over the cosine. So typically we're going to use the negative ln of cosine. Notice I started with x, and because I just jumped right to my antiderivative, I stayed with x. So there's no reason to change our limits here. We're not doing u substitution at all. This is now a known antiderivative. We're just going to plug in the upper limit, lower limit, and then whatever this evaluates to be is going to be our answer. So we will get the natural log, oh gosh, x coordinate at 60 degrees is a half, minus the natural log cosine of 0 is a 1. So we for sure, we've done it 3 times today. Natural log is 1 is 0, negative ln of 1/2. If you wrote this, totally fine. On a test, quiz, multiple choice, it definitely is going to get written as the natural log of 2. So just again, make sure to remember all those log properties from a couple chapters ago. Okay, good. I think we're actually going to get the last couple done. So 23, one more log. As soon as you see this, we're rewriting it. Whether it's a derivative or an antiderivative, you're going to rewrite a common log all the time. So the natural log of 2 stays the same. And then that log base 2 we're going to write as the natural log of x over the natural log of 2. And then all of that has a denominator of x. And then very nicely, the natural log of 2's cancel. Then this becomes a nice, easy problem because you just have ln of x over x. And then it's pretty obvious then, hopefully, what our u is in our process. So u is the natural log because the derivative will give us a 1 over x and then the dx. So the natural log of x is your numerator. So initially that's in our numerator. And then you so would have had this 1 over x and the dx. But all of that, this 1 over x dx would get rid of everything else by just replacing it with a du. So all we really end up with, as this all disappears and gets replaced by a du, is just a u du. We now do need new limits because we did go from x's to u's. So we're back to using this to convert. Take your 1, plug it in, and the natural log of 1 is 0. Take your 4 and plug it in. Nothing good happens here, so you just leave it as the natural log of 4. And then antiderivative, upper limit minus your lower limit. And then this is obviously 0, that'll go away, and this ends up being our answer. All right. Then, mercifully, our last u substitution of these notes, number 24. Pick your u. Hopefully this is obvious, but it's an uglier function. It's an exponential that we haven't dealt with a ton. And then the real test is, could you do the next step? So if you think you know your u, your du, and your substitution, see if you could do kind of the second and third step also. Okay, let's make sure we got off to the right start. I have the u. It's got to be just the natural log of x. We don't want the 2 to be any part of that. Derivative then gives us the 1 over x dx. So pretty much everything is accounted for between the u and the du, except our 2. So it's just the 2 raised to the power of u. And then the x in the denominator and the dx will be gone when we substitute in the du. Take the x, convert it. So when I plug that in, u is now the natural log of 1, which is 0. Take the 2, plug it in over here. Nothing nice happens there, so you just have to write it as the natural log of 2. Again, be prepared on quizzes and tests to just stop right here. It allows me to give you some more problems too. So sometimes I just want you to stop there. If we continue though, now we need to remember this antiderivative. So this is our exponential function. It's going to repeat itself. So you're going to get that 2 to the u again. And then now we have to divide by the natural log of the base. So in this case, the natural log of 2, as well as whatever the coefficient of our u was. It was just a 1, so you don't necessarily need to show that. But if there were a coefficient, we'd want to divide by that. So this ends up being our antiderivative, 2 to the u over the natural log of 2. And that's kind of what I wanted to see if you remembered. And then from 0 to the natural log of 2, plug in your upper limit, lower limit. Whenever I see this problem, I feel like good stuff should happen here, like something should happen here. There's so many 2's and log rules and whatever should reduce. But alas, nothing happens. So that just remains a weird 2 to the ln of 2 over the natural log of 2. I'll write it as one fraction now though, because this has a denominator of 2 as well. 2 to the 0 was a 1, so we just end up with 2 to the ln of 2 minus 1, and then all over ln of 2. Right? That's u substitution. I try to do a couple of every type of a function, exponentials, logarithms, common logs. Usually by the end of those 24 problems, we're feeling pretty good about everything. The last thing I want to do, 26. Don't worry about 25. Like, you should be able to do it, but probably only have time for 26. And here's why I want you to be able to do 26. It's what we just tested on. I give you a second derivative. I want you to eventually give me the original function. So if we do the antiderivative of the second derivative, that's going to give us the first. And then we get our plus c. We then want to figure out what is the c for our first derivative. So here I tell you that your first derivative has a value of 3 when our x is pi over 4. So let the derivative be 3. And let the x be pi over 4. We've done this once today. The tangent of pi over 4 we said was 1. So our first c ends up being a 2. That allows us to rewrite the first derivative in its entirety as the tangent of x plus 2. Then we need to do one more derivative or antiderivative to get to the original function. And then here's the reason I wanted us to do this one. When I now do this antiderivative, you're going to get f of x. And then again, like I said earlier, now that we have done this, now that we have done the antiderivative of a tangent, you are going to see this increasingly more. We haven't seen it before then today because it's u substitution. This is already a long problem, right? We're already 5 or 6 steps in. We've still got a number of steps to go. You don't want to have to do u substitution for this in the context of doing all the work for the original problem. We want to be able to know that right away the antiderivative of tangent is right at the negative ln of cosine of x, and we can make this a whole lot shorter. And then plus our 2x plus our c. If you're going through u substitution now, this just becomes a nightmare. It's already so much work, it just becomes more. All right, but with that, now we plug these in. Our functional value is 2 pi when x is pi. So these 2 pi's are just going to cancel, so that's nice. And then we get what? Negative ln of negative, oh, that's nice. So it ultimately becomes a natural log of a positive one, that's a 0. So our c equals a 0. So in reality, this was our answer here, except we just don't need the c anymore because our c was a 0. All right. Good, we kind of got through that, a little rushed. So the quiz is going to be on, I'm planning to do the quiz on Tuesday. The homework is going to be due on Monday. So the homework you can find on Canvas again, if you just click on the assignments tab. Hey, there you go. You'll see it embedded in there. You can just click on that. If you don't have a printer, there's, I think, probably about a dozen problems. Just write them, do them on a plain piece of paper. Okay? Okay, that's all I got. If you have any questions, there's a minute. You can stick around. If there's any that you weren't sure about. But if you're good, then take off. Have a good weekend. We'll see everybody on Monday. Say that one more time. It should be 2.